Hello, Geometry. Chapter 6, Lesson 1. We are starting the last chapter before we've reached the midpoint, the midway of the textbook. So our goal is to hopefully get through all the way through Chapter 12, and so we'll be halfway there once we get done with this one. And so this one is going to be dealing a lot with angles and circles and triangles and kind of putting all those different things together here. So 6.1 talks about perpendicular and angle bisectors. Now, if you remember, bisector is basically an object that splits something. It's an official word. Splits something into two equal parts. So we're going to have perpendicular bisectors and angle bisectors are the two that we're looking at here. And I'm going to show a few things on Desmos geometry here. Bisector of an angle. So perpendicular bisectors, bisector of an angle. This is page 164. Before we get going too much, the word equidistant, I think we've heard that before. And that means it's the same distance from two different objects. Same distance from two different objects. Textbook says a point is equidistant from two figures when the point is the same distance from each figure. Okay, so a midpoint would be something that is equidistant from the endpoints on a segment. Okay, so this is the first one we're going to look at here, perpendicular bisector theorem, and we're going to make that sort of diagram over here, so you get to watch me do the whole thing. You can definitely practice on your own. So I'm going to make a segment, and I want to find, check this out, this might help out, there we go. I want to find the midpoint of that segment. Hey, there it is. Okay, that's under More Tools, and now I want a perpendicular line, so I'll select the line, then I'll select the point, and I have a perpendicular bisector. Okay. So I want to show you that it is a perpendicular bisector. I'll turn the distances on. So you can see that is 2.81. No matter how wide that is, that line stays as a perpendicular bisector. So what happens when you have a perpendicular bisector? Our theorem here is going to say if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay? So I have to put a point on my perpendicular bisector, so I'll just put another point right there. And they say no matter where that point goes, whether it's up high or really close to it or down here, the distance from that point to these endpoints will always be the same. So my question there is, what type of triangle is it showing you? If those two sides are going to be the same length, you should have an isosceles triangle. Okay? So if you have a perpendicular bisector and a point on it, you're going to have an isosceles triangle. So no matter where I've moved that point, it's always going to be the same distance from both of those. Okay? And the converse is going to be true as well. So this was our perpendicular bisector theorem. Okay, if a point lies on the perpendicular bisector, then it's equidistant from the endpoints of the segment. So if I know I have a triangle here, and I know that is congruent to that, and this is a right angle. So this is a perpendicular. You have to have a right angle. So you must have a right angle, R-I-G-H-T. And it must go through a midpoint. Must go through midpoint. Then you have an isosceles triangle. Okay. So if this is 10 inches and this is x, you know that x has to equal 10 inches. Okay. So the converse, remember the converse takes the conclusion and makes it into a hypothesis. So if we have a point that is equidistant from the ends of the segment, then the point lies on the perpendicular bisector of the segment. So in a plane, if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of the segment. Okay? So since D is the same distance from B as it is from A, it's going to lie on line CP. Okay? So D lies on CP since it is the same distance from A and B. So we could say it is equidistant from A and B. Okay, so that's our perpendicular bisector theorem. Our second set of theorems for today, they're called the angle bisector theorem. If a point lies on the bisector of an angle, so now we're bisecting an angle, we're not bisecting a segment, then it is equidistant from the two sides of the angle. So what that looks like, let me save that one, and let me pull up angle bisector. I already have this one made, took a few more steps. So the angle bisector theorem, if a point lies on the bisector of an angle, so AD right here is my bisector of an angle. So you see the two angles there at 21 degrees. So D lies on that bisector. Then it is equidistant from the two sides of the triangle. So then D, they're looking at this mark right here. Okay, that one and that one. See that 2.68? Since D is on the angle bisector, those distances are going to be the same. Now notice the distances have to be measured making a right angle. When they refer to the distance, they're referring to the shortest distance, which will always make a right angle. Now if I move D, you notice those distances always stay the same. So for any point on the angle bisector, it's going to be the same distance from this one as it is from this one. Okay, it makes a shape called a kite. So that's what the angle bisector theorem is showing us. Let's make this 20 degrees and this 20 degrees. Okay, it has to form a right angle. Let's say that's X. It has to form a right angle, and this is 8.28 inches. Okay, so we know X has to equal 8.28 inches. So the converse, of course, is going to take the conclusion. You'll have a point that is equidistant from both sides, and that means it lies on the angle bisector. So since the theorem and its converse are both true, that means you could write it a biconditional statement using if and only if. So a point lies on the angle bisector, a bisector of an angle if and only if it is equidistant from two sides of an angle. So that takes the other direction. If I move this around, let me show you that. Okay, you notice this point is always the same distance from the two sides. Okay, D is staying the same distance, and it's always going to stay, this angle is going to change no matter what. It's kind of fun. Make a square. At some point you have a square. About there. Okay. Enough playing around. Back to work. So the converse of the angle bisector theorem, here you are given a point, let's write that word, equidistant from two lines, then that point lies on the angle bisector, or the bisector of the angle. Okay, so our examples here. This is page 168. Find the indicated measure. Explain your reasoning. Alright, so we have a triangle here. Looks like we have a perpendicular bisector. And this is 9. They want the length from A to B. So they want this side right here. Well, since A lies on the perpendicular bisector, it's bisecting because those are both 6. If that's 9, we know that AB has to equal 9. Explain your reasoning. We're going to use our theorems to explain that. And we would say because of the perpendicular bisector theorem. Perpendicular bisector theorem. It lies on the perpendicular, so it's the same equidistance from both of them. Okay, EG, this length right here. So F, this is perpendicular, and F is the same distance from G as it is from E. So that means it has to lie on the perpendicular bisector, making this 3, and so EG has to be 6. That would be the converse of the perpendicular bisector theorem. The converse of perpendicular. It's converse because you're starting, you have these two sides, and then you're finding the perpendicular bisector. On one, we had the perpendicular bisector, and we're finding the two sides that make it isosceles. Okay, so R, get some algebra here. R is the point that is equidistant from the two endpoints, so it's going to be a converse. And we know that 2x plus 2 has to equal 3x, minus the 2x over, and you get x equals 2. So x equals 2. They want us to find the length STU. So if I go 2 times 2 plus 2, I get SU to equal 6. Or 3 times 2 would be 6. You notice they're both 6 on either side. So again, we were given the point that is equidistant. We are working with the segment that is being bisected. So we're going to use the converse of the perpendicular bisector theorem. Okay, so we have one example here. So pay attention to this. This is kind of a little algebra review. It says find the equation of the perpendicular bisector of AB. Okay? So the first thing you need to do is find the midpoint of segment AB. Okay? So midpoint from segment AB. So their midpoint, your x is going to be x1 plus x2 divided by 2. So in this case, my x values, A is at 0, negative 2. B is at 2, 2. Okay? You can kind of look at this too and see, okay, midpoint should be right there. So here's a formula. X is x1 plus x2 divided by 2. So that's 0 plus 2 divided by 2. That's going to be 1. 2 over 2, which is 1. My y value is y1 plus y2 divided by 2. That's negative 2 plus 2 divided by 2, and that's 0 over 2, which is 0. So my midpoint is at 1, 0. 1, 0. Okay? Now we want the perpendicular bisector. This slope, we need the slope here. So the slope of AB, the line AB, equals up 2 over 1. 2 over 1, which is 2. Okay, so the slope of line AB is up 2 over 1. You can use the slope formula, y2 minus y1 over x2 minus x1. But remember, we want the perpendicular slope, and that is going to be the opposite reciprocal. So it's positive 2 over 1, so our perpendicular slope is going to be negative 1 over 2. And once you get your perpendicular slope and your point, remember point-slope form. Y minus y1 equals m times x minus x1, where your midpoint is going to be the x1 and y1, and your slope is going to be negative 1/2. So I get y minus 0, there's y1, equals negative 1/2 times x minus x1, which is 1. So clean that up, y equals negative 1/2 x plus 1/2. 1/2 x, negative 1/2 x plus 1/2. So if I go that would be my perpendicular bisector. Y-intercept of 1/2 and the slope of negative 1/2. Okay, so a little quick review with that, with algebra. If you have some questions on that when you get to it, please let me know. Exercise 5 through 7, find the indicated measure, explain your reasoning. You want the measure of angle CAB. These are dealing with angle bisectors. So CAB, you see how this is equidistant. D is equidistant from C as it is from B. So if that's 20, that has to be 20, measure angle CAB, the big angle would equal 40 degrees. They don't just say 20, they want the big angle. And this one, they gave us that the distances were there. They're asking for the angles. This would be the converse of the angle bisector theorem. Converse of the angle bisector theorem. Okay, so here we know we have an angle bisector, AD is bisecting or bisects angle BAC. It's 30 and 30, so if that's 5, DC has to equal 5. And that's the angle bisector theorem. And of course, they have to throw the letters back in there. Okay, you see these arcs, that means these are congruent angles. So 3x plus 1 has to equal 5x minus 1. So bring the 1 over there, minus 3x to the right. That cancels, I get 2 equals 2x, so x equals 1. Make sure we answer the question. They want BD. So if x equals 1, this would be 3 times 1 plus 1, which is 4. So BD equals 4, and we are using, they gave us that the angles are congruent, so we're using the angle bisector theorem. Okay. That wraps up the instruction for that. Again, there's examples with the equation for perpendicular bisectors. This is page 305 in the textbook. This is what you're looking for. They're giving you a segment, and you're looking for the equation of the line that goes through the midpoint and is perpendicular to it. Okay, so you have to use perpendicular slopes, opposite reciprocals. Okay. So a few applications with that also occurring in the assignment, but you'll let me know which questions you have. I'll see you in class, and good luck.